Well, thank you everyone for attending this webinar. It was kind of put together maybe a little bit quicker than normal. I just talked to Steve, I think it was basically last week. I said, hey Steve, we're doing a lot of cool stuff with RTK and PPK capabilities within CPC. Can we set up a webinar? And he emailed me back the same day and said, hey, you're set up in a week's time. We put together this presentation because, like I mentioned to Steve, we're kind of seeing a little bit of a shift. As you all know, the drone industry is evolving very, very rapidly, and it's very cool to see. And one of the things that we're kind of seeing now is that a lot of people are starting to invest in some of these drones that are PPK and RTK capable. Okay, and the big I guess the elephant in the room would be DJI, who released a Phantom 4 RTK drone, I think back in October of last year. But there's a whole bunch of other people that are coming online, a whole bunch of other manufacturers that are coming online with solutions like this. And it's very interesting as we're building PhotoCapture and incorporating this better data, and we're seeing some of the results and what can really be achieved with RTK capable drones from a photogrammetry standpoint. So that's what this webinar is about. So let's get started. As always, the point of these webinars is to learn something. So, hopefully, whether or not you have a drone that has RTK or PPK capability, or you do not have one, you'll get something out of today's webinar and be able to apply it immediately if you already own one, or in the future if you decide to invest in one. All right, so some of the technical goals, we're going to go over what is RTK and PPK. You've probably heard those terms quite often. We're going to talk about why RTK and PPK can help improve the mapping accuracy that you can achieve with your drone. And we're going to talk about some of the technical considerations with RTK PPK. And I think if it's okay with everyone, for the sake of my own for the sake of pronunciation, I might just blend RTK and PPK together and call them RPK. Well, maybe not. I just don't want to keep saying RTK, PPK all day. But so we're going to talk about, do you need GCPs? If you have an RTK system, a lot of people are hearing, well, hey, I don't need GCPs. Why? The whole point is to get rid of GCPs. And so we'll talk about, whether or not you need ground control points. We'll talk about checkpoints. What are checkpoints? Do I need them? And we're also going to talk about camera calibration and relative and absolute accuracy. And the last part of this is we'll go over a couple case studies to kind of show you what's possible with these systems. And as always, with these webinars, we love the tech, right? We love the technical side of things, but at the same time, we also recognize that you're all trying to operate businesses and make money, and so we're going to try and go over, what from a workflow perspective, how can these RTK and PPK capable drones, sort of improve your workflow, or maybe allow you to do jobs that maybe traditionally you weren't able to do. Okay. So that's always, part of these webinars, or at least it's our attempt to provide some of that content. All right. So before we get started on all of the technical stuff, I wanted to go ahead and show you some of the new features in CPC. And actually, even before that, so before we go over this, like Steve mentioned, these webinars, we want you to get something out of them. So if you have any questions, feel free to ask them in the bottom right-hand corner of your GoToWebinar control panel, or I'm not sure how it looks on your end, but there should be some form of place where you can ask questions. And if you have any questions as we go along, please don't hesitate to ask. That's what we're here for. And it's likely that if you have a question, someone else is thinking the exact same thing. And so it's better off for everyone if you ask the question. So just to go over what's new in CPC. So CPC is Carlson PhotoCapture, and it's the photogrammetry software that Carlson offers for essentially turning images that you take off of your drone into mapping products. Okay, so when I say mapping products, I'm talking about ortho photos, dense point clouds, digital elevation models, etc. And so for those of you familiar with PhotoCapture, I wanted to go over some of the new features that we released recently. So we've got improved orthophoto edge quality. So you can see here, looking at these high-walled buildings, you can see the edges of the buildings much better, much crisper. We've got improved dense point cloud quality. So we made a change to our algorithm, and it's producing much denser, a little bit denser data than before. I know some people say, hey, quit it with the density. We want less dense data, not more dense. But we're also working on making that configurable for you as well. But as you can see, we're producing great quality point clouds. I'm not sure if you can see it in this image. It's a little bit grainy at least on my full screen monitor, but the quality is excellent. Here's another example, just for reference. And we're producing it at a much larger scale. So we've had a couple projects recently that are upwards of 700 million points, 800 million points, and so you just get a feel for the tremendous volume of data that you can capture just with a drone and a camera. It's just incredible.
Hey Ben, we have a question. Yep. They were wanting to know if those point clouds that you were showing were nadir flight only.
Okay, so this one actually was a nadir flight. It was fairly high overlap, which is why you can see the sides of the building pretty well. This one, however, was captured at what we call the ideal mapping angle. And as you can see here, this was about 30 degrees, 35 degrees off nadir. And so you can see all the sides of the buildings. You can even see the telephone poles and the transmission lines going through the project. So generally what we recommend is, if you want to get building facades, if you want to model those well, we recommend capturing imagery with an off nadir angle of about 30 to 35 degrees. Because if you go too far off nadir, the quality, the overall quality of your point cloud does start to degrade. But there's like the sweet spot where you can get all those vertical facades, but not really have any degradation of point cloud quality, and that's in that 25 to 35 degree off nadir range. So that's our recommendation. But very good question. I wish I actually had some slides in this presentation, and I took them out that actually went over that. All right, the next thing is in the new features, we have a more streamlined RTK drone workflow. And so I'm going to talk about this today mainly. But just a couple of quick examples of why you might consider using RTK. RTK on the drone really helps to improve the network stability and make your the overall accuracy of your project really what you're gaining is consistency. Okay, so you know you're much less dependent on the spatial distribution of your control points. You just end up with much more consistent consistent data, and it sort of allows you to yeah, really focus on, you know, checking the data quality, you know, using checkpoints and validating the accuracy of your map. But for what it's worth, now in CPC, we actually automatically identify most of the popular RTK drones. So if you have an RTK capable drone like a DJI Phantom 4 RTK, CPC will actually automatically recognize that it's RTK, and photogrammetrically it's going to use those positions more accurately. It's going to say, hey, I know that the photo centers or the photo positions coming off this particular drone are very accurate, and then it's going to use that in the photogrammetry solution. And we're getting great results. You know, we're getting, and I'll go into that later on, but we're getting, you know, this is in centimeters or in meters, of course. So, you know, we're getting around a tenth, sometimes even less on the vertical accuracy, vertical and horizontal accuracy with RTK data sets. The last thing, or the last couple things that are new is faster processing. So everything's distributed now and it goes much, much faster. And there's also a project quality report. So you can, you know, identify everything that's going on in your project that you process, validate the accuracy, etc. Oh, and then one last thing, the introduction of the survey canvas. Okay, and the survey canvas is sort of a way to digitally survey on the 3D models that you generate from CPC. Okay, so it's a new feature. You can, you know, measure 3D polylines. You can grid surfaces, create, you know, different types of line work directly on the 3D models. So it's really cool, and we encourage you to check it out. All right, so let's get into the meat of today's presentation. And so the first thing I'm going to go over is what is RTK and PPK. Okay, so RTK and PPK, it's you know, GNSS positioning technology, and it's characterized by the use of carrier phase observations. Okay, so for most of you surveyors out there, geodesists, you know, you're already using, you're probably already using RTK for your base and rover out in the field. So the only difference now is that the receiver, instead of being, you know, the rover on the ground, the receiver is now on the drone itself. Okay, and to do that, you need, you know, you need to be recording dual frequency observations. So you want multiple frequencies to help resolve some of the GPS ambiguities, and you also need carrier phase observations. But if you have one of these dual frequency receivers, it's possible to achieve centimeter level relative accuracies. Okay, so RTK stands for real-time kinematic, and PPK stands for post-processing kinematic. Okay, and so just to go over kind of the difference between RTK and PPK. So RTK is like it says on here, or what we said back on this slide, real time, right? Real time kinematic. So what happens is, you know, both the base station and the rover are simultaneously recording GPS observations. With RTK, the base station is sending via a radio link. You know, it's sending those observations to the receiver, to the rover. Okay, so the rover gets those observations. It calculates the solution based on those rover, or based on the base observations. So it uses a double difference measurement, and it calculates its position relative to the base station. Okay, and this is very important because we're going to go over a couple case studies where you can see how this can get a little confusing and you can mess things up if you're not careful. Okay, so always remember that with RTK and or PPK, it's always relative positioning. So you're setting up on a known, it's only the rover, it's computing its position with respect to the base. Okay, so if you don't know the position of the base, then effectively you don't know that. If you don't know the absolute position of the base, you don't know the absolute position of the rover. Okay, sorry about that. Everything is relative to the base station. Okay, so the RTK drone must stay connected. With RTK, the rover has to stay connected via the radio link to the base station while it's gathering data. Otherwise, that RTK breaks down, right? You lose, if it's not getting the data fast enough, you lose that RTK lock. Okay. And you lose the positional information during the time where you lost that radio link. Right. Maybe it's your connection, Steve. Just it's a possibility. All right. So like I mentioned, everything is post-flight. All right. So you bring the observation files down onto your computer, and you might wait a couple days to get a more accurate, GPS. GPS observations from like NGS, for example, better, more accurate Rhinex files. But everything is done post-flight, okay? So that's the biggest difference between RTK and PPK. So when you hear RTK, those corrections are being sent in real time, whereas with PPK, you're waiting until after the flight to process your baselines, okay? Those baselines between the GPS receiver and the drone. And this is, again, we want to stress with both of these methods, okay, what you're solving for is that baseline vector. And I know this isn't about geodesy. That's not the point of the presentation today. But it's important that you remember that because it comes up time and time again. Okay, so when you do either PPK or RTK, you're solving for the baseline between those two receivers, not the absolute position. Okay, so you need to set that base up on a known point so that your relative corrections to the drone are going to be with respect to that known point. All right, so the summary, what is RTK and PPK? So RTK is real-time kinematic. All right, everything's in real time. You're sending corrections over the radio. PPK is post-processing kinematic. Okay, so generally, what I say is, most of the time you're going to be utilizing, PPK, post-processing after the flight. It's just not always necessary to have RTK, but those are the differences between the two. Okay, both are relative positioning, right? So you're solving for the baseline between the base and the rover, and they're both characterized by high accuracy carrier phase dual frequency observations. All right, so now that we know what RTK and PPK is, we're gonna talk about, hey, can I? And this is the question that always comes up: is if I've got RTK, or if I've got a drone that has this dual frequency receiver on it that's capable of RTK and or PPK, I don't need ground control points anymore, right? Because now every photo I take is essentially a sky control point, right? So we hear this quite a bit, and let me just kind of go over what's going on there. Okay, so a standard drone platform like a DJI Phantom 4, you can see here on the right-hand side that the positional accuracy of the Phantom 4 and most other commercial drones, it's about 5 meters. Okay, now with an RTK PPK drone platform, you're getting down to 2 centimeter accuracy on those position estimates, okay? And so, what's happening is, you've got a much more, like I said, you essentially have sky control. Instead of ground control, each photo that you take essentially is a sky control point. But that doesn't necessarily mean that you do away with GCPs, and we're going to go into describing why. So we've gone over this before, but with ground control points, if you're using a standard drone platform like this, okay, one that's not PPK enabled, the spatial distribution of your ground control points matters a lot, okay? So we showed you some bad examples before. So here's a couple examples. This one's down in Maysville at Carlson, where we've got 5 control points, but the spatial distribution is very bad. Okay, another example, only 4 control points, not very well distributed throughout the project area. And then this last example, this is much better. This is a better distribution. But as we all know, that distribution of control points matters, okay? So when the drone accuracy is this bad, the spatial distribution matters, because if the drone accuracy is that bad, there's not enough ground control points throughout the project. Like, for example, on this northwest side of this project, those positions, the ground surface that we estimate is sort of going to, it's going to be floating. It might have a tilt to it or a skew, okay? And or a bowing effect. That's what we call it, is a bowing effect. And so what you can see happen is that the 3D surface can wiggle between the control points. So it might be very good near the control points, but in between them, if there's not a good spatial distribution, you get this wiggle effect, okay? And so in this slide, the green surface is what I've estimated with photogrammetry, and the black surface is my true ground surface, okay? And this is something that we, it comes up for a variety of reasons. So poor camera or lens calibration, that's a great example. If you're dealing with a very flat scene, like a field, for example, something that has very little vertical relief, you can often see this drift if your ground control points are spaced too far apart. Now, with RTK, remember, if we use that sky control concept, it's virtually impossible for the surface to wiggle, okay? And that's because each camera position now becomes a control point, okay? And we call that, sky control, okay? So with RTK, because we know the position of each camera location very accurately, it's almost impossible for that surface to wiggle. So what you end up getting, is a much more accurate surface, a much more consistent surface. So even if you have a poor distribution of GCPs, or not that many of them, this is where these RTK drones really shine, okay? Because it doesn't really matter, because you have, each photo position in the sky is a control point. Now, there is a caveat to that, and I'm going to go into that next. But generally speaking, what you'll see is immediately, your horizontal accuracy, even if you don't utilize ground control points, is very tight, okay? And like we said, that's because of the fact that we have essentially sky control points. But what you can see, and this is something that comes up a lot in like user forums, and people are encountering it more and more as they invest in RTK drones, is that if you abandon GCPs while your horizontal accuracy is good, you end up with a vertical bias, a simple vertical offset in the data set you process. And we're going to show you a couple examples, okay? But either way, what I like to say is, a lot of manufacturers now say, hey, with an RTK or PPK capable drone, you eliminate GCPs, okay? And we say, fiction, that is not true, if someone says that, you should be very wary of anything else that they say, okay? Because it's essentially you are the one that's going to be liable if you abandon the use of GCPs, and then you end up having a problem. The second thing is drastically reducing field time. This is a true statement, okay? Because you can reduce the amount of control points you have to set dramatically by using a RTK drone. Fully automated, I don't necessarily know. I mean, there's still some checks and balances that you as the surveyor, you have to go in and verify, right? Hey, is this map as accurate as I'm expecting it to be and what I'm saying it is? Okay, so I wouldn't say it's fully automated. It's up to you to have a system of checks and balances in place. Okay, so let's just go over a couple industry trends. So what we're seeing now is kind of a shift into more automation with the drone platform. Okay, so I'd say where we are right now is in the middle, where we're utilizing drones, and it is increasing job site automation to some degree because it's just reducing the amount of time we have to spend in the field, and it's collecting a lot of that data autonomously for us. But we still need to pilot out flying the drone on site, and of course, there's even in the past, I saw a couple news releases in the past couple of days of companies that are, very much, they're ready to fly autonomously, basically a drone in a box, right? So the drone stays on the work site and flies the work site on a daily basis, and you just control it from the office. Now, what we're also seeing is that besides this drone in a box concept, all of the major manufacturers are coming out with RTK capable or PPK capable drones. Okay, so the Phantom 4 RTK from DJI. You can also get some of their higher end models with RTK as well, like the M600. The Unique, they've rolled out their H520 that has RTK capable RTK capabilities. SenseFly, Loki, there's a whole bunch of different vendors who are realizing, hey, we need to put this on each of our drones, okay? And so in my opinion, I think this is only going to accelerate. And at least within the surveying industry, what you're going to see is that every drone offered will probably have RTK capabilities on it going forward. It's just so it's just a very valuable asset to have. So some of the, like I mentioned, many of the main manufacturers are. Oh, it looks like we've got a couple questions. Steve, well, let's see here. Looks like audio is fine. Okay, these are all pertaining to the audio. Excellent. All right, so going back to the presentation, some of the platforms, like I mentioned, DJI, Unique, SenseFly, GeoQ, they outfit, they do custom outfitting of drones with their Loki platform. So there's quite a few different vendors who are offering this capability. Okay, and if you just do a basic search, you'll find different examples of these vendors. All right, so let's get into some of the technical considerations for these workflows. And reminder, if anyone has questions, please answer them below. Okay, so using GCPs with RTK and PPK drones. Okay, so again, this is some of the things you hear that you just have to you can eliminate GCPs as soon as you buy this equipment, and we want to show you why that's not true. Okay, so if you abandon ground control points, what happens here is that you horizontally, right? Remember what we mentioned, horizontally, the accuracy out of the box with an RTK capable drone on your ground control point targets or checkpoints, you're going to see that it's usually going to be plus or minus a couple centimeters. okay? But what you'll often see, and we've had several people, comment on this, is that, hey, if I'm not using any ground control points, I, even though my horizontal accuracy is very good, I can see a small vertical bias, okay? And that bias might be anywhere from 10 centimeters up to half a meter, right? You don't know necessarily. And so everything looks good, right? The data looks beautiful. Horizontally, it's very accurate. Everything fits into place. But when you actually get into the 3D surface and you look at the vertical component, you see, hey, I've got this bias that's consistent across my whole project. Okay, so if you were just to say, if you were to not use ground control points and just say, hey, I'm gonna go out, fly my RTK capable drone. It's gonna do everything for me. This is awesome. I don't have to worry about GCPs anymore. Well, you're gonna have some serious, you're likely to have some very serious liability issues. Okay, because it's very possible that without GCPs, you can run into this vertical bias offset problem. Okay. So, like I said, this vertical bias with RTK platforms, horizontally, it's very good. For various reasons, this vertical bias can come in. Okay, it can be from the calibration of your camera. Okay, so that's one issue. So that's issue number one. Your camera just isn't perfectly calibrated. Issue number two could be that there's just a datum mismatch between your ground control network and your the network that you're using for the RTK. Okay, so and so this is why it's so valuable to have checkpoints and even ground control points, because at least with ground control points, you can remove that vertical bias. Okay, and you don't compromise anything. You just set one or two control. We recommend 2 control points to best solve for the vertical bias, but that's all you need on the project is 2 control points, to solve for that vertical bias. We recommend having more checkpoints, but at least to solve for that bias, all you really need is 2 ground control points. And like I mentioned, down at this bottom left-hand corner, I put it in red. If you don't do that, if you just fly it as is, and you're doing survey work, and people are trying to match up elevations, past elevations to present observation elevations, you're going to run into issues. All right, so checkpoints. I'm actually going to show an example of this on a live demo at the very end of this presentation, so I won't go into it. But the next thing is, so regarding this vertical bias, using a calibrated camera. And this can really just, RTK is going to dramatically, it's going to give you great consistency over the project. That's its biggest benefit, is the consistency you're going to achieve from an accuracy standpoint. But you can also improve both your RTK workflow and non-RTK workflow if you do camera calibration. Okay, and we're actually working on putting together a calibration guide for everyone using CPC, and you can do it indoors or outdoors. But outdoors, it's rather simple. You just pick a structure with a lot of vertical components to it, if possible, and a lot of texture. So maybe this example isn't great, but otherwise I would shoot for like a brick building with a lot of vertical relief, and in the middle of a parking lot, like a bank, for example. And all you need to do is fly. You really need to fly at 2 different altitudes. So maybe one flight at 100 feet, another flight at 175, and those can both be vertical or nadir collection. And then the last thing for camera calibration is, pitch your camera up 35 degrees and fly the same mission. And that, when you pitch your camera up and roll it, that decouples some of those calibration parameters and allows you to get a much better and consistent estimate for camera calibration. Okay.
Hey, Ben,
Yep.
question on that. Wondering how often the camera should be calibrated.
That is a good question, and I wish I had a good answer. So, if everything goes well, if you don't bang your drone in a truck or have a crash landing, or if everything's going without a hitch, conventionally with photogrammetry, people are typically calibrating, once a year. Now, with a drone platform, it's a little bit more, how do I say it, less robust than maybe an airplane, an airplane system. So I would probably I would start off, definitely with once per year, and then depending on how much you abuse it, maybe increase that, maybe do it a couple times a year, and just make sure that your calibration is staying, the same values, right? You don't want it to be changing significantly, because that indicates that something may have changed. Maybe it was a crash landing, maybe it was something with the lens. You never know, right? But ideally, those calibration values should be very consistent. All right, so we're getting towards the end. We're getting towards the meat, I should say, and going over a few real world examples. So we've gone over quite a bit of theory already, right? We've gone over what is RTK. We've talked about relative positioning. We talked about ground control points. Now here are some issues with relative positioning, okay? Oh, we're gonna get into the case studies. I'm sorry, forgot about that. So let me show you a couple case studies that we have, all right? So we have two that I brought up for the presentation today, all right? We have the California project, and this consisted of 189 images, 4 GCPs, 3 checkpoints, and the base was set up on a known GCP, or it was set up on a measured point. So part of a control network. So that's data set 1. The second one we have here is from Australia, and we'll call this data set 2. And it's about the same size. It's 183 images, or 173 images. In this case, there's only 3 ground control points, okay? And the GCPs were met, and this is something to be aware of. So the base was set up on a unknown point, okay? So if you recall, RTK, remember, it's relative positioning. So what this user did was he set up the base, and he was broadcasting those corrections to the drone, okay? But he just set up the base on an unknown point and let it cook for a while. But the issue, well, I won't get into that yet. But those are the 2 main differences between these data sets. They're about the same size. One had 3 GCPs, the other one had a little bit more about 4 GCPs and then 3 checkpoints. Okay, so going back to this first example, the California project, and I'll bring the actual data set up here in a second. So as you can see here, everything. This is in PhotoCapture. This is the sparse point cloud where we're looking at the accuracy of the aerial triangulation. And you can see here that with the ground control points and the checkpoints, everything is green, okay? And this is good. This is what we want to see, okay? And so for this checkpoint that I've got highlighted here in green, you can see that. And so a checkpoint is a ground control point that's not used at all in the photogrammetry adjustment. Essentially, it's completely external. It's completely independent, and we only use it afterwards to check the accuracy of our solution, okay? So you can see on this California project, the checkpoint error is, horizontally, we're talking about 1 centimeter, and vertically, we're talking about 3 centimeters. Okay, so just a little over 1/10 vertically, and so that one was excellent, right?
Ben,
Very.
we've got a question here. I'm not sure I understand. It should the accuracy of GCPs and checkpoints be the same?
Ooh, good question. With RTK capable with an RTK capable drone, or an RTK or a PPK capable drone, yes, the accuracy of your checkpoints and the accuracy of your GCPs should be very, very similar. Now I'm not saying they'll all be 1 centimeter exactly, right? You're going to have some variation, right? Maybe plus one, 1.5 centimeters here, 2.5 there, right? But it should all be in the same ballpark of, in my opinion, 5 centimeters or less, because they're essentially like I said, with RTK capable drones, these are sky control points. Okay, so you've got a bunch of control points in the sky, you've got control points on the ground, you've got checkpoints. They're all using the same carrier phase measurements. They're all using the same type of observation. So they should have similar accuracy. So what you should see is the error on your ground control point should be, within, we'll say 5 centimeters. The error on your camera photo stations, like the estimated camera positions, should be in plus or minus 5 centimeters, and the error on your checkpoint should be plus or minus 5 centimeters as well. Does that make sense? Hopefully. Okay, so that was the California example, and as you can see, it produced some beautiful data. Yeah, it just worked great first try. The second one is this Australia project. So remember, in this scenario, the base was set up on an unknown point, so not on an existing network, and the RTK corrections were measured with respect to the base. So what we found out was that during the initial bundle adjustment stage, all of the photo positions were we had a very high relative accuracy. Okay, so before we introduced any ground control points, all of the photo positions were, like I mentioned a couple minutes ago, they were all within plus or minus 5 centimeters of the photo position that was given in the log file. Okay, but then what we found out is that when we added the ground control points, so we brought in these 3 ground control points, we added them, and we were like, what is going on here? Why are my ground control points, why do they have an error of up to 1.5 meters? And it was driving us crazy, because we've been working with the DJI drone quite a bit. It had been producing, for a number of users, really good data. And then in this particular example, the difference between the ground control point and the estimated position of the ground control point was 1.5 meters off in X, Y, and Z. And so we were like, what is going on here? And so we started a dialogue with the user, and what we found out was, like I mentioned, the base was set up on an unknown point. Okay, so in this diagram, the base was not tied into the existing the existing network. So even though the corrections to the drone were all very accurate, so the drone positions, the relative positions from the drone to the base were all 5 centimeters, we were having this big offset issue with the ground control point. And so what we found out was that if we added an additional parameter to Carlson PhotoCapture for RTK data sets, and what it does is it says, hey, if you have a base if you didn't set up on a known point, we're going to calculate a 3D offset between the base location that you gave us, or the ground control point location that you gave us, and what we're estimating from the photogrammetry. And so when we added those new parameters to to the code and checked it, we were within, we saw this, every ground control point was checking within plus or minus 3 centimeters. And so it was wonderful, and we were so happy that, hey, we figured out what's going on. Everything has to be tied into the same network, okay? So if you're using ground control points, make sure that if you're doing RTK with the drone, that your base station is tied into that same network, so that you don't have this offset issue between points, or between your ground control points and your drone positions. Okay, so that's a great example of what was happening there. The relative accuracy of the drone positions were wonderful, excellent, but when we tried to tie it back to the ground control points, we had this bias, this offset problem. Once we figured it out, everything matched up very, very well, and that's what it should do. And that's really, again, that's the beauty, that's the beauty of RTK capable drones, or PPK capable drones, and also the beauty of photogrammetry is that they complement each other so well. Okay, because we can identify issues in the data directly, because we know that, hey, the quality of these photo positions should be this accurate. The quality of these ground control points should be this accurate. And if they aren't, we know that there's a problem, So then it just becomes a matter of figuring out what that might be. So it's really, really nice, because you can sort of narrow down what these issues might be, or what they might be due to. But the last thing I wanted to say was, if we didn't have ground control points for this project, okay? So if we would have just not utilized those, what we would have seen is, in the bundle adjustment, we would have seen that all of the photo stations were as accurate as we expected them to be, right? They would have been plus or minus 5 centimeters. We would have said, hey, this looks great. But if we would have actually provided that data to a client, and they would have compared it to an existing survey, they would have said, hey guys, we're busting by 1.5 meters. What's going on here? Okay, and so that's why I say, ground control points are so valuable, and checkpoints are so valuable, because they help you identify, issues that you didn't actually know were existing in your data. It looked great, but when you actually, got down to brass tacks and comparing it to existing surveys, you run into problems, and that's where having ground control points really helps out. All right, so just to summarize, RTK on the drone helps to improve the network stability. Remember, consistency. So you don't have to worry about spatial distribution of ground control points. You don't have to worry about the edges of your project being less accurate, because you don't have ground control points out there. With RTK, it really alleviates that problem. Depending on the terrain, like I said, depending on how varied the terrain is, how well calibrated your camera is, this can be very useful. And the price tag for these, for having an RTK capable drone is going to make up for itself very fast, very quickly, just because you're able to, you're not worried about checking the data all across the project area. You can or measuring a bunch of control points at a bunch of different places in your project. It's much less of a need from a ground control point distribution standpoint to collect a whole bunch of them. And the last thing I was going to say is, you can measure the same amount of control if you want to preserve your workflow, but you can use all of those points as check shots. Okay, hey, I expect my map, my 3D point cloud to be within 3 centimeters. I'm going to use this control point as a checkpoint instead, and verify that CPC is doing what it's supposed to, and that my accuracy is within this range. Okay, so that's the beauty. That's why, that's my pitch on why RTK and PPK can be very valuable. All right, the last thing I'll say is that CPC automatically recognizes the most popular drone RTK models. You can estimate you can set the estimated accuracy of your drone system in CPC for better stability, and you can help, CPC, the photogrammetry can actually help you figure out what aspects of your RTK system aren't performing adequately, or like we saw in that Australia project, where did things go wrong? Okay, so that's, it's very, very valuable on big, large-scale projects. So I would say yes, large productivity gains can be made with CPC and PPK, RTK, PPK workflows. So thank you, everyone. That's the end of the presentation. There's about 5 minutes left for questions. Please ask away.
Well, Ben, thank you very much. I don't know if people are typing questions or not. We'll see here in a second. If the attendees note, there is a link for, if you're not a user yet, there's a demo user link down in your, at the bottom of your GoToMeeting screen there that you can sign up for 5 free gigabytes. And as you guys get RTK drones and have questions, you can jump on the CPC chat line, and Ben or Zach or myself and others will be able to answer your questions real time. Jim, go ahead and ask your question, please.
Yep. Yeah, the stone wall isn't the boundary. No.
Having a little trouble hearing you, Jim. If you would repeat that question.
Isn't there one on the plot line?
I think maybe he's on the phone, potentially.
Hold on a second. Let me just pull it up. I'm pretty sure I thought I put a dimension on it.
Oh, is that me then thinking?
Yeah.
Still mic in this. Right? What? I thought it was good.
All right, so I'm picking up a few questions here.
No, it's
yes.
not.
So Gus will have access to the rest of the webinar.
Hold on a second.
I'm going to mute Jim. Gus, you will have access to the webinar. We're going to put up a video on YouTube, so we'll send you a link. Will there be a CPC webinar soon? Vern, can you tell me about that? What you mean exactly? I can show you how CPC works if that's what you're asking. We'd be happy to do that.
Vern, you're live.
Oh, well, maybe he's not ready either. And then the last question is from Gus. He says, can you get 1 centimeter vertical accuracy? 1 centimeter, what I would say, Gus, is that, that's going to be tough, only because the accuracy of GPS observations in general, especially kinematic observations, is really plus or minus 2 centimeters. I know some, if you sit on a point for a longer period of time, it might get better. But you got to remember, this is kinematic. The drone is flying, right? People are moving around. You don't have that opportunity to sit on a point and make sure you're getting maybe sub 2 centimeter accuracy. So I can't say that you wouldn't get 1 centimeter. I mean, it's possible, but I wouldn't guarantee that you will get 1 centimeter, if that makes sense. Just because the accuracy of the observations themselves is not, consistently 1 centimeter. If anyone
And yes,
wanted,
we will be having more Carlson PhotoCapture webinars. We're hopefully going to have a series of them here coming up. I was talking with marketing about that today. So yes, Vern, we will stay tuned. We will be doing a complete series of CPC webinars that'll take us through basics into the survey canvas, advanced settings, etc.
so I apologize. This was, I ran out of time. I wish I could have gone through the workflow in CPC. We've had a lot of questions regarding RTK and PPK drones that I kind of wanted to set the record straight on some of this in more of an educational webinar setting. But we'd love to show everyone here how to, and maybe we can set that up next, but basically how to work through a RTK project in Carlson PhotoCapture, from start to finish, and see what kind of results we can generate.
The new parameters for the offset PPK locations.
Oh, Carlos, yeah, those are, we're working on that. It's coming up in our next release. We're working on building the user interface to allow them to determine whether or not they want to use the offset. But it'll be in our next release, our next major release. It will be 99% likely it will be in the project configuration page. When you upload and it asks you about your advanced settings, we'll just have you mark that the offset PPK in that advanced settings page. All right. Well, thank you, everyone. I appreciate your attendance to the webinar. If you have any questions, like Steve mentioned, let us know. We know this one was on a little bit short notice. Maybe didn't get enough emails out there to everyone, but we hope you enjoyed it, and feel free to contact us. Thank you very much.